Good afternoon, good morning. My name is J Prendergast, so I'm going to present this work on behalf of an array of co-authors, some of which are in the room. So I will say at the start that if there's any complicated questions, I'm already going to give your attention to those. So this work basically looks at SHM and how design code compliance works for performance assessment of bridges under combined hazards, so the combined hazards of scour and seismic. So just a small introduction to it. So bridge failures which are induced by natural hazards tend to be increasing. This is a function of the aging bridge stock internationally and climate change effects and other such effects that are making these failures occur more frequently. So this contribution looks at flooding and earthquakes, so flood-induced scour and earthquake effects and their combined actions, and how they can be considered quite a critical load case for damage causing. So flooding and scour effects predominantly affect substructures of bridges, which has ramifications for the bridge foundation itself, but also secondary effects with other damage happening at the superstructure level. And combined with this, in seismic-prone regions, induced ground motions from earthquake motion can affect bridge elements which can be exacerbated due to scour. So the combined effects can actually be a much more critical case than the two effects alone. So a small introduction to scour itself. So some of the typical damage scenarios that can happen due to scour really depend on the type of bridge you're looking at and the type of system in place. So scour itself is in effect the erosion of ground material from around the foundation of an element. So for a masonry arch structure, for example, this can have ramifications for arch stability. For a flexible abutment pier integral bridge type system, it can have an effect on the flexibility and the dynamic motions. Your failures range from total catastrophic sudden failure, which can be seen in some of the images on the bottom here. Is a pier settlement which has rendered the bridge unusable, but it hasn't actually been a full collapse. So the damage scenarios due to scour are primary and secondary. The most primary or straight up element of damage is damage to the foundation elements itself. So in the case of pile foundations, for example, when you have an array of scour, you will lose your lateral support, and that can cause pile buckling at a very local level. But this has secondary effects for the superstructure as well. So a buckled pile renders the foundation compromised, and that can affect your superstructure. So your deck will undergo excessive cracking, excessive movement, settlement, serviceability failure, and different things like that. Other secondary effects can occur due to differential settlement of different foundations in multiple span bridges. So if you have loss of support or loss of stiffness around one particular bridge element, that can lead to a propagating effect across the structure where you'll get crack formation at different critical connection points. As well as that, then that depends on whether it's a local pile type failure or whether it's a pile group failure or even just tilt, unacceptable movements, and effectively, depending on the type of bridge, these effects have much different effects. For seismic actions, the effects are much more well understood in the case. So you'll have collapse of piers for bending or for shear actions due to the influx of an earthquake motion. Total collapse of pier foundations. You can also have loss of deck unseating and things like that can happen just due to the motions of the bridge itself under the seismic action. So what I will look at in a moment is how, when you have scour with a seismic action, how that can exacerbate these effects and bring a situation to something that wasn't that particularly unsafe to something that becomes quite critical. So the structural health monitoring for seismic actions are broadly based into two specific areas. So you have your subjective, what I'm going to term subjective visual-based assessments, where you assess a structure post-event to see what kind of damage situation you have. The damages are this could be quite disadvantageous in the sense of it's extremely time-consuming. To know where the damage is already is the most critical way of doing it, but it's also quite resource intensive. So it takes a lot of man hours and a lot of time, and for a damaged structure that's out of operation, this can be very critical on a network level. The more objective-based system will be a sensor-based approach where you have online damage detection systems, for example, accelerometers or other vibration sensors, which can detect losses in stiffness or cracking or other damage that occurs post-event for the rapid assessment of the structure. And it's completely based on the response of the structure itself, so it's a much more advantageous system if it can be operated correctly. So for Scour, the structural health monitoring is broadly similar in the sense of the vibration-based aspect, which I'll discuss subsequently. But aside from that, the most common way that Scour is assessed still internationally today is by visual assessment. So divers physically go down into the waterway and they assess what the condition of foundations are and look for damage elements. It's highly subjective. The rating schemes can be quite variable, and they depend a lot on the different agencies that are implementing them. So for the sensor-based approach for Scour itself, there's a wide array of different sensors that are available, some of which are shown here. So for example, simple systems like float-out systems, which you implement into the soil in front of a pier, for example. When Scour occurs, these systems float out of the soil, they trigger an electrical signal, and that lets the bridge manager know that the Scour hole has reached that depth, for example. Other more complicated arrangements are to use ground-penetrating radar or time-domain reflectometry systems, which also require either intensive manual use or they have to be installed into a riverbed, which is labor intensive as well. And I'm just going to give some background on the vibration-based approach. That's my own background. So we've developed a tool for performing sensitivity analysis on vibration-based Scour detection methods. So this is a vehicle bridge soil dynamic interaction model, which we've programmed to be able to simulate the effect of Scour on a two-span integral bridge loaded by a vehicle which incorporates realistic vehicle input forces and allows the user to output dynamic signals for a range of Scour conditions. The purpose of this model is to enable researchers to develop vibration-based methods, either time or frequency-based, to assess how sensitive these parameters are to Scour and see if these can be implemented on real structures as part of a maintenance regime. So the bridge itself that has been programmed at the moment is limited to a two-span integral bridge, but it's actually quite malleable in the sense that you can investigate the effects of soil density, effects of different soil area and vehicle velocity effects, the effects of where you place your sensors, how the various modes of typical bridge structures are affected by Scour at variable locations. And this can also be extended to other bridge types as well. So one such study that we have looked at to date is, can you locate a Scour hole around the structure by simply analysing the dynamic response from a variety of points on the structure? So shown here is a simple two-span bridge with 4 accelerometers shown. The model itself is capable of inputting a road profile which simulates how rough the road surface is, so if a vehicle drives across the road, the forces that the vehicle imparts into the structure are more realistic of a real vehicle. Your output accelerations then can be analysed to see how they vary point to point on the structure due to Scour at different locations, so either around an abutment or a particular pier. And one such finding from this model has been that Scour actually has a very local effect on flexible abutment type structures, where if you scour the left-hand side abutment, for example, the mode or the mode of vibration that relates to that particular element is highly affected by Scour, but absolutely unaffected by Scour elsewhere. So using this information about the structure allows the user to actually see where the Scour hole has occurred, as opposed to assessing if there is Scour at all. So not only will it say, yes, we've lost stiffness due to Scour, but it will also say, we also have Scour at a point on the structure. So just some background into the design code of compliance for performance assessment for seismic actions. Seismic actions are split into two particular different methods. So that your performance-based design is either force-based or displacement-based, and this is several different target parameters depending on what you're trying to look at. So in terms of compliance for seismic actions, the Eurocode 8 is the most broadly used one currently, and also there's some mention of the Italian codes as well, has some mention in it, but broadly speaking, it doesn't seem to be in a lot of the design codes, and it's actually quite difficult to get information on where all this stuff is. So there are some limitations on this, and if there's any questions in this particular aspect, I will draw your attention to some of my colleagues, because my background isn't in seismic actions. But just on Scour assessments due to design code compliance, Scour has an effect at the design stage insofar as it is seen as a critical design scenario, so there are a range of methods used to design for it for a new construction. So one of the findings of this paper was that there's a broad range of different design approaches used to design for a scour hole. So I mentioned some of them there, like the CSU method or the HEC-AD. And some of the things that we found is that to design a scour hole depends on the situation where the bridge is to be constructed, and it depends broadly on the flow conditions, geometry of the structure, the type of soil, the soil conditions themselves, the amount of debris that's expected in a channel, as well as natural channel evolution effects, and you end up getting a wide variety of potential likely scour holes under an input of these parameters depending on which method you're using. But what we have found is, broadly speaking, national authorities who own the bridges tend to implement their own type of systems to design for these. But in effect, it's post-event as opposed to pre-event is how scour is mostly looked at these days. So for old aged structures, generally you're looking at retrofitting it for scour. So these design methods, although they're great for initial preliminary design, they're not that relevant for assessing an actually existing structure due to scour. So in terms of the joint actions of seismic and scour effects, one of the more potentially better approaches is to use fragility curve analysis, which will give you a probability of a failure occurring for a given intensity of scour, depending on your situation. So the graph shown there just shows the probability of a failure of an element under an array of scour depths, depending on which limit state that you're looking at. And if we're looking at a situation where we're implementing seismic with scour and the potential ramifications of the loss of stiffness due to scour with the movements expected under a given ground motion due to seismic actions, this may be the most reliable method to look at. So just to conclude, a lack of preventive maintenance and monitoring has caused a lot of collapse of bridges. Also, climate change effects and increased flooding and natural disasters is still causing massive problems for our bridge network, as well as the fact that our bridge network, broadly speaking internationally, is aging and becoming more damaged over time. Combining hazards, obviously enough, is actually a more critical case than not. So for a seismic prone region, the seismic design of a bridge might be fine on its own, but if you scour one of the elements, the redistribution of stiffness and the redistribution of stresses could actually become a much more critical load case. And on that, I'll conclude. Thanks very much.
Thank you, Luke, for a very nice presentation. Is there any question?
Up there, yeah.
First, I introduce myself. My name is Dimitri Diamantinis. I'm working in the Technical University in Regensburg. My question regards the probability of failure. Is it considering of a member, let's say, of the bridge or of the whole bridge due to the scour? Because we have morning from other presentations that the system reliability is considered, for example, that is my question. Is it at member level or at the system level of the bridge?
Well, I haven't done any research on it per se, but so the example I gave is just an example of how it can be applied. So it actually can be applied at any level. So a local element for a foundation, you can do a reliability analysis to see how that would be affected by a given scour depth. But you could also do it up to a full bridge level or even a full network level. So I don't know if I'm giving you a proper answer. This isn't my background, but
okay.
Generally speaking, anything you want to do,